All right, so what we have said so far is that we are able to build a matrix M where each row represents a word or a term X, and we have for each value represents the distribution of this term across context. And we have a similarity measure that allows us to compare these words and see which ones are more similar than others. In the previous example, we used the verb objects of co-occurrence, but we will see now that we can do other things. I mean, obviously, you can use the immediate lexical context or whatever you want, depends on the application. So there are many different models that we could choose, but we have to know why we choose a model and what do we hope to achieve with that. Different models can capture different types of similarity, and we want to see, or we will see in this video, how you can vary a couple of things to obtain the results that give you the type of similarity you're looking for. Before doing that, I would like to ask a question, and we will try to discuss it in class. And it's an important question in my opinion. So we said we have this matrix M here that we discuss over here, and each row represents a word. Okay, each column has a value that the whole thing is the distribution across context. So if we have here the word dog, and here the word love, and here the word like, and here the word cat, let me add one more column here, one more row, sorry, and we have the word horse over here, then using my similarity measure, I should see that these guys are more similar to each other than these, versus these are more similar to each other. So this solves my problem that we discussed. I don't remember if it was the first or the second video, because now if I have a training corpus that has seen I love dogs and has seen I like cats, and now it says in the test sentence is I love horses, even if it has never seen horses before, by looking at these values here, which is what it is going to use to classify, they're going to be very similar to these guys, and so there is a high chance that our classification will be correct. And hooray, we have solved, like, partially solved the problem of unseen words. Okay? But now, that's what this is trying to do, and it does it pretty well. I would like you now to, this is my question, to take the other side of the argument and try to say, well, what are the things that are bad about this? All right, we have seen a lot of linguistically motivated concepts and issues that motivate NLP so far in this course. I'd like you to use that material, everything we talked about, like for example, we talked about ambiguity in language. Could you discuss this matrix M under for ambiguity? Does it solve the problem? Yes, no. If yes, how? If no, why? Does it make ambiguity worse sometimes? Probably, I don't know. What about multi-word terms? This is something that we discussed partially when we were doing language models, because we said, well, the probability of a word given the history, etc. Well, if we have a multi-word term, then maybe the probabilities will help capture that properly because you have seen it in the corpus. But let's say that you have the word hot and you have the word dog. Let's say that you grew up in a planet where they don't have hot dogs. There is no way actually that you could infer from these two words what a hot dog is, right? Because dog is an animal, hot is a temperature value or estimate, and hot dog should only mean that a dog is hot, right? You couldn't possibly infer that hot dog is food. All right, so what if we look at this? How does this treat this problem? Does it treat this problem at all? And if it does, how? And there are other things. There are other things that I would like you to sit down and think about this. Like, let's say I'm going to use this in a real world problem. What is it that I'm going to miss? Okay, there are at least 3 obvious points. Here are 2. There is a third one. But then if you think about it more, you can come up with 5 or 6. And I would like to discuss them with you in class. All right, moving on. So, okay, how can you vary this? Well, the most obvious thing is that you're going to pre-process your text. Because whatever we have been using to compute the count of the co-occurrence, we can use the word form, but we can use the lemmas too. So the count of run and horse does not get split from the count of run and horses, right? Because if you take the lemma, this is going to disappear and these 2 counts will become 1. You can use the pause tag. Why would you use the pause tag? Well, because you want to sometimes differentiate between like when it comes as a verb, when you say, you know, John likes his Mercedes, or when you use like as a preposition, when you say apples are not like oranges, okay? If you don't do this, then your co-occurrence matrix will consider these 2 as one word, and that's not going to be very accurate. So you can use pause tags if you want. But here again, you should think about why and why not you should use these. So this is another point I would like to discuss with you in class. All right, so then you can also change the way in which you define your context. So far we said we're going to use syntactic dependence, meaning verb object. I could have used verb subject. I could have used noun and adjective modifier. I could have used noun and noun modifier. So many things I could have used. I could choose to remove stop words or keep them. Or I could use actually the word context instead of the syntactic dependent, the lexical context, the words around the word that I'm looking for. All right. And when I choose all of this, I should choose also what is the size of the context window. I can take my word and take the 2 words before the 2 words after, or I can take the 20 words before and the 20 words after as a context. All right. Another thing is term weighting, and we'll talk about this in a minute, because when we said we take a word, so let's say that I have a word wi, and then I have wi minus 2, wi minus 1 in a sentence, and then I have wi plus 1, wi plus 2, etc., etc. And let's say that I'm taking a context window of minus 2 plus 2. So that means that in my co-occurrence, I'm going to see how many times wi co-occurs with any of these words. All right. And I'm going to take as my window minus 2 plus 2. But if I do that, I am just considering that all the words are the same, right? So this word is as important as that one, the other one, or the I plus 2. In term weighting, we're going to say, well, maybe they're not all the same. Maybe I'm going to add a weight to this in order to give one more importance than the other. You can normalize your values. I talked a little bit about this before, because it's always a good idea. Dimensionality reduction, you can do that. There are a couple of ways you can do this. We'll talk about them later. One of them is using, matrix manipulation kind of operation like SVD. Another one is to use neural models. And then you can vary your similarity measure if you want to see if one of them gives you some advantages over the other. All right. So first of all, there are 2 types of semantic relatedness, so 2 similarities. So relatedness, we call it syntagmatic relatedness, so words that occur nearby each other but are not necessarily similar. So you have car and drive, you have car and tire. Meronymy is something we're going to talk about in the next session when we talk about semantics. And then you have paradigmatic relatedness, where you basically can substitute one word for another, like you have car, automobile. Hypernames is also something we're going to talk about in the next session in class. You have car, vehicle, etc. So how would you define distributional context to capture each of these similarities? One way to do this is that actually when you vary the window, you capture different types of relatedness. So for the word dog, for example, if you use a two-word window, you get things like cat, horse, fox, bat, etc., which are all different animals, versus if you use a 30-word window, then you have different types of dogs, right? And you even have properties of the dog. All right, so this guy sneaked in, kind of, in comparison with the others. Okay, so maybe if you, well, not maybe, but when you vary the context size, you capture different types of relations. Now, as we said for the term weighting, it's not a good idea to just consider that all the words are similar. And because all the words that appear in the context do not really help you classify a word or measure the similarity of that word to others. So you might want to do something about that. And this is why, this is because, according to the Zipfian distribution that we have seen, I think, in the first lecture or the second, and we can remind it here, if you take a corpus and you compute the frequency of each one of the term, and then you plot them here, you will see that you have words in the middle, like the middle frequencies here, that actually are meaningful words, and they are very, very related to the main topic of your corpus. If there is one, maybe there is more than one main topic, it depends what kind of corpus. Then you have the very rare ones, and usually they're not very helpful, right? Because you can't see a pattern there if they appear so infrequently. And usually they are like named entities or some, multi-word hyphened term, etc. Maybe sometimes a typo if you have like a social media corpus. Sometimes there are typos are all rare over there. And then you have the very, very frequent words, and they are all stop words. Okay. So what you want to do is that you want to be selective about this, because words like the are not going to help you really to show that two words are more similar to each other. Okay. And these words here, maybe they are very semantically grounded because they are named entities, but they appear so infrequently that maybe it's not going to help you much. So how are we going to weight these terms in order so that I can give to one term more power of decision of what semantic category this word belongs to than others? We're going to use something called TF-IDF. All right. So TF-IDF normally is used in document retrieval. So you have the term frequency, and then you have the inverse document frequency. And when you are doing information retrieval, what you are trying to do is you have a set of documents. So this is D1, D2, D3, and somebody has a query. All right, so let's say that the query is one word, like for example, IBM, or no, not IBM, not a good word. Boom, boom, boom. Okay, let's use IBM. Okay, so IBM is cheap. Let's say that we are talking about stocks. All right, and these documents here have a bunch of words in them, each one of them. Okay, so now you have to represent these documents in a way that when I have a new query, I can compute similarity between the query and each one of these documents, and then I can return the document that are most similar to the query. All right, but words like is are not very important. Why? Because each one of these documents has a high chance to have the word is appearing a bunch of times. So the word is, in technical terms, we can say is not very discriminative. It doesn't help me to see which documents I want to look into. All right. How am I going to capture that in my measure? I'm going to compute the invert document frequency. I'm going to say in how many documents does the word is appear? It actually appears in all the documents. Okay. But I want to take the inverse of that because I want the document to be weak, or I want the document to not take into consideration those terms. when it computes the similarity. All right, so I want my similarity measure to not take very much into consideration the word is. So if the word is appears in all of the documents, then that means that the document frequency is high. So I'm going to take the inverse of that because I want it to be very, very low. Okay. Versus words like IBM, which appear only here, for example, let's say only in this document, are very important words because they help me discriminate which documents are more important than others. But now, in this context, we're going to use the inverse document frequency, or TF-IDF, differently. We don't have documents here. What we really have, we have one big document, and we have a bunch of words, okay? And what I'm going to do is I'm going to go to each one of these words, and I'm going to take a context of -2 plus 2, let's say. We should say -n plus n generally. So I'm going to take the two words before and the two words after. And this word in the center is going to be my target term. Okay, this is T. All right. And each one of these is going to be a document. So document is the target word D. Oh, sorry. The target term is D. And each one of these is T. All right. So what I'm going to say is, first question I'm going to ask is, for example, let's make this bigger here. So I have word I minus 1, word I minus 2, word I plus 1, word I plus 2. So I'm going to say this is my term D. And I'm going to ask the question, how many times these two co-occur together? All right, this is the count. This is the TF that I'm looking for. Okay, and then I'm going to actually ask the question about, well, what about other words that WI minus 1 appears with in the context? If WI minus 1 is a word like, for example, the, that means I'm going to find a bunch of other words that it co-occurs with. If the word WI minus 1 is a different kind of word, like for example the word run, then I'm not going to find that many words. I'm going to find at least much less than the word the. Okay, so this means that this is more discriminative because it helps me more identify the semantics of this word than this word here. And then I'm going to do the same thing as we said here. I'm going to take the inverse of that. So what I'm going to do is assign a weight on each one of these words. All right, before I put them in my matrix M, the distributional semantics matrix. Yeah, so I'm going to assign a weight of each one of this. This weight is going to be the product of TF and IDF. So first, I'm going to say how many times does this word co-occur with my target word. And then I'm going to say, well, let's count all of the other target words D that it co-occurs with, which is what this expression here means. And then I'm going to normalize. I'm just going to count all the target words D. All right, I hope you see this. So then words like run, I'm going to have a higher TF-IDF than, so this is a higher TF-IDF than words like the. And so when I add them to the matrix, the column that belongs to the word the is going to have small numbers because it doesn't help me distinguish, and so I'm penalizing it. Okay. All right. So other things that you can do, and that we're going to talk about next, is that these co-occurrence matrices, they tend to be very sparse, right? Because words don't co-occur with other words, all of the other words in the corpus. So you're going to have a lot of zero entries. This is bad in many ways. First, your matrix is too big, so it's inconvenient to store, slow computation, and we still can have a lot of orthogonal dimensions which are irrelevant, but we keep them there. So numbers that are stored and we compute with them all the time, but they never help us do anything good. All right, so We're going to talk now about word embeddings. And in word embeddings, we're going to make this representation in a low dimensional dense vector space. All right, so we're going to get rid of all the noise, get rid of all the orthogonal dimensions, and we're going to make the thing more compact. So you can do a matrix decomposition like SVD or PCA even. And there is a beautiful paper that compares this to neural models. And what you can do is you can do neural networks. And this is what we're going to talk about in the next video. I'm going to try to post, or maybe I can, if you remind me in class, I can show you a paper where they take, when you use neural networks, you can do it in many, but we'll see how you can do it with the word-to-vec approach. And then if you use matrix decomposition, you can use PCA. And there is a beautiful paper that shows you that actually if you do PCA, plus you add some constraints when you do your PCA, and plus some hyperparameters, then you get exactly the same results as word-to-vec. Why is this an important paper? Because before that there was another paper called, if I remember well, something like predicts don't count. And I think it was by Marco Baroni, if I'm not mistaken, which he showed that predicts, which is what word-to-vec does, is much more powerful than count, which is what PCA does. But the second paper by Omer Levy, if I'm not mistaken, it's a Tackle paper, which is a journal, Tackle, but I can get you the exact title, etc. if you are interested. All right, let's jump into neural networks in the next video.